All right, guys, we will be looking at adders and subtractors. I believe Dr. Rahul, he showed you some aspects of adders yesterday, right? You have started off the topic of adders yesterday, and today we will be looking at subtractors. All right, we will be looking at subtractors. All right, let's have a second over here. Okay, let me just log in to the Moodle shell. And tomorrow evening is the mid-semester exam, and that's at the big lecture room. That's why I didn't have it here, because we can use the big lecture room for your mid-semester exam. All right. And the mid-semester exam covers everything up till yesterday, but also if you attend today's lecture, it does help because adders and subtractors, they overlap. The type of material involved is they overlap. All right, now all right, guys. So I'm going to assume that you were here in yesterday's lecture, and we will continue our studies of adders and subtractors. Right. So the whole idea. Okay. So some of the things which we are looking at. You see, up till now, what we were doing was we were looking at basic building blocks. We were looking at basic building blocks of digital electronic systems. So you learned about AND gate, OR gate. You learned about Boolean algebra, Boolean theorem. These are, and you learned all these different tools, Carnot maps. So you learned about the blocks, like the basic fundamental blocks, which are all the gates and how they function. The universal gate, how do they interact with each other, how you can put them in combinations, parallel series, all these sort of things, right? Then we learned about, of course, before that we learned about the number system to be used in that block. Then we learned about all these tools. We learned about different ways of looking at circuits. If you want a two-level circuit, so it's either product of sums or sum of products. We learned about Carnot maps. We learned about Boolean theorems. Now we move into application, right? And one of the first things you want to apply digital circuits to is an arithmetic circuit, right? There's really no point in lighting up LEDs and all that, right, if you can't do greater level of usage of our digital and Boolean circuits. Now, the digital and Boolean circuits which we've learned so far, all the basic gates and all the theorems, we want to apply it. And we want to apply it to build circuits such that you can do arithmetic. You can do arithmetic logic, all right? So what do we mean by arithmetic logic? You want our digital electronics to crunch numbers. You want to add. You want to subtract, right? You want to do the hard calculations. Because if you can't do that, that's the whole basis. That's the whole basis of us building a computer. Because inside the computer you have a CPU, right? You have also got now a GLU, graphics unit, right? Graphics unit is made using arithmetic, a number of arithmetic logic units, right? Okay, so sometimes there's two separate parts. The ALU is separate and the graphic unit is separate. There's RAM, there's memory. So what we're working towards is, I'm not saying that at the end of the semester you will build a computer. I'm saying you will know how different parts of the processor works, how to build it from scratch. How did it come about, right? So obviously we started off with simple things like AND gate, NOT gate, right? And you will be saying that who built the AND gate and NOT gate? Well, that's why you will be doing this course called EE212, analog electronics. So it starts off with analog electronics. You have things like transistors. I'm pretty sure you may have just started something called bipolar junction transistors or something along those lines. And then have you moved on to FETs, field effect transistors? Right? Okay, so after BJTs, you'll move into FETs, and after FETs, you'll move into MOSFETs, And then from there, you will build AND gates using transistors. So AND gates, NOT gates, OR gates, all these things are built using transistors. Once you get those gates done, then you put gates together. You put a couple of gates together to make a circuit. Now, what we are now starting off yesterday, is we want to show you how to build arithmetic circuits. So yesterday's lecture was on half adders. Half. Right? Okay? Today's lecture is on half subtractors. Half subtractors. Let me just see if I can download here. Okay, show all downloads. All right. Put a control X and download documents. Put control V. Doesn't come in. Okay. Okay. Let's do a quick recap of yesterday's lecture. So, half adders. So we went through the fundamentals of adding, you know, all the rules. You wrote some things in your book about the truth table. This is a circuit of a half adder, right? This is a circuit of a half adder, all right? And then we did a full adder. We did a full adder. All right, now, what is the difference between a half adder and a full adder? Now, the difference is a half adder can only accommodate, two bits to be added, two single bits. So you have one bit plus another bit, right? Okay, it can only accommodate that much, right? And 2 bits, guys, 2 bits, that means if you are adding 2 bits, where do we go? What is the maximum number which you can cater for? Well, 2 bits, the maximum answer, the largest answer, possible answer you can have is the number 2, right? But even then, you have, as you looked at your half adder, you have something called carry out and a sum, okay? So that's why it's called a half adder. Then, in order to expand the system, so you link a half adder up, so they very nicely name this thing as a half adder. You link one half adder up with another half adder to make a full adder. Now the full adder, the advantage is, it can extend the range. The full adder can extend the range, right? It can extend the range, and therefore you also had a carry out in half adder, but full adder you can now have for your sum can then carry 2 bits. In your half adder, the sum could only carry 1 bit, could only hold 1 bit. I don't want to use the word carry because in our system we have something called carry, right? So in a half adder, our sum only had the capacity for 1 bit, and the carry was another bit. Sometimes carry would become overflow. So as your system becomes larger, if you want to do a real sum, like for example, 5 plus 5, right? So that's what? 5 is 101 plus 101. The answer is 1010. How do we implement that in a circuit? So you've got to think along the lines of how many bits can be carried, how many bits can be held, how many bits do you need to process. So therefore, you make your system as large as possible to cater for that. So then there's something called full adder. This is a full adder, right? 2 half adders. But even this full adder has got a limitation. What is the limitation? The full adder has a limitation such that, what? It can only hold 2 bits. The sum is capable of 2 bits. So again, we run into some sort of problems, right? Okay. So in the end, you've got to, the way out of it is, you've got to daisy chain. The word is daisy chain. The word is you've got to link up a lot of full adders together. You've got to link up a number of full adders together in order to make a very large system. So I want to show you this. Look at this circuit. So where did we start off from? We started off from just the baby, just a little XOR gate with an AND gate there, right? And this was only to cater for this much. That circuit can only cater for this much. right? Okay, it can do this very neatly, can do the second line very neatly, can do the third line very neatly. The final line, there is a carry out of 1. The answer is 0, the sum is 0, and the carry out is 1. So it was able to handle that. But who does a 0 plus 1? In real life, when you want to crunch numbers, you're going to do some real heavy-duty crunching. Like, for example, if you've got an FX, your Casio calculator, right? Okay, you do some real crunching. And then, of course, if you've got a graphics processor, right? A graphics processor, that's doing even more crunching of graphics. Graphics is just numbers in the end. You decompose any image, the way it works is, okay, let me give you one more example of where this is applied, right? This circuit and this circuit, right? Basically, this circuit is in block diagram format. This is the logic circuit. Every picture is constructed using pixels, right? One pixel has got 3 values to it. Every pixel, red, green, and blue, right? And it's giving you, so every pixel has got three groups of data, 3 sets of data to it. So if you have, let's say, a pixel dimension of 1024 by 720 dimension pixel image, right? Let's say it's a JPEG image, right? So it's got 1024 times 720 pixels in it, right? That's the dimensions. Okay, now, then every pixel has got three colors, red, blue, green, RGB. And it will say the component, what is the level of R? How much R? How much G? How much B, right? RGB. Then, so if R is sitting at 115, G is sitting at 210, and B is sitting at 076, that comes out to be a particular type of color, right? So every color which you see is decomposed into 3 of its components, right? Okay, every color which you see is decomposed into 3 components, right? Okay, now, then, when you want to do some kind of, let's say, filtering, or you want to do some kind of graphics processing, right? You want to do some sort of scaling. So you have to play with those numbers. So in the end, those numbers have to be processed by some kind of logic circuit which does number crunching. I'm not saying it's going to be using a full adder circuit. No, it's going to be using some very large circuit. How do you build a large circuit? So I want you to see the pattern here, guys. The pattern is like this. We started off with a very basic, this is the block diagram of a half adder, 2 bits going in, 2 bits coming out, sum and carry out. This is the same thing, but you're finding out what's inside the blocks, right? Remember, why did we present this in a sort of a block system? Is because we want to reuse it. We want to recycle it, right? So something like, if you remember lab 3, there was something called a macro, because you want to reuse it over and over again. You don't want to redraw this over and over again. You just create a block, then you can recycle it. So then you have this. Then we realize, hey, that's only 2 bits. We can only do sum of 2 bits. But in reality, we need to do much more. How do you extend this system? So we do something like this. We put 2 half adders together in this particular way. The carry from here comes here, the carry from here comes here, and then you are fusing the 2 half adders together. This is important. Then this becomes our final circuit. But then again, this has got limitation. So at every stage in time, you will have limitation, right? This can only add 2 bits, right? You've got a sum and you've got a carry, but it can do slightly more. But now you have another input called carry in, another input. So our half adder, the difference between half adder and full adder was, half adder does not allow for carry in. Full adder can. So I will now present to you another circuit which I drew. Have a look at this. This is a 4-bit parallel adder. This is a 4-bit parallel adder. So you would have asked me, well, but the full adder and the half adder still do only addition of 2 bits. Right? Doesn't make any difference. The only difference was in the full adder, you have a carry in allowed. Now, because we have built up the architecture in that way, you have a 4-bit parallel adder. A 4-bit parallel adder. And by the way, guys, this is, I think this lecture all gets recorded on the, what do you call, on the lecture capture system. So you'll see this diagram, right? Okay, so this is a 4-bit parallel adder, guys. Take note of this, right? So can you see, what is the catch over here? The carry out of the first half adder goes into the carry in of the second full adder. The carry out of the second full adder goes into the carry out of the second of the fours, and it continues. All right? Okay. So this is how you build it. And of course, so this is called scaling the system. This here is how you scale digital logic. When we learn about digital logic, of course, I'm going to teach you 1 plus 1, right? How to build the 1 plus 1 circuit. And then I said one step further, how to accommodate a carry in. Once we accommodated the carry in using the full adder, we can then scale. That's the key word in engineering, scaling the system, right? Once you know how to do a 4-bit, then from there, if I say, hey, I've got a 32-bit number, or I want you to use build a 32-bit machine to process this image, you should be able to. So if you have one image and you want to add another image, right? That's how you're going to do it. But of course, not with 4 bits. You might use a bigger number crunching machine. So this is a 4-bit system. So this should be able to do 15 plus 15, right? Or 12 plus 10, something like that. Okay? All right. Now, based on this lecture, we now move to another lecture. Based on this lecture, we now move to another lecture. And guys, these PowerPoint slides are all available on the Moodle shell. Okay, so yeah, this is the keyword. What is the difference between half and full subtractor? So let's talk about subtractors now. Same concept. Remember, if you notice this course, everything is repeating itself. Everything repeats itself, except for we just add one more item to it. All right? Okay, so if you looked at how we did, let's say, conversion of binary to octal and binary to hexadecimal, you see the concepts are the same. It's only that we've changed one particular variable, right? And if you look at all the theorems, they were all just rotating with each other, and they were all tied into each other. Same thing goes here. So if you can learn what do you call half adders and full adders very well, half subtractors and full subtractors should be a very easy system for you. Okay. All right. Now let's start off with the basics. If you wanted to do 25 minus 18, you would first go from the right hand side. From which side? I wouldn't call it the right hand side. We're doing digital logic over here. We'd say we go from the least significant digit side, right? We attempt from the least significant digit. So we say 5 minus 8, and you say, oh, can't do that because 5 is a smaller number. So what do? In normal primary school mathematics, you go next door, right, to the 1 digit up, right? You do something called a borrow. You all remember this, right? You borrow a 1, and it's left over with a 1. So you borrow a 1, so that becomes a 15. 15 minus 8 is 7, and 1 minus 1 is 0. But we don't write 0, 7. We just say the answer is 7, right? But of course, for the purpose of our electronics, we will get some zeros. So I want you to note something over here. There is 2 words. Firstly, there is something called borrow out. There is something called borrow out, and there's something called borrow in. So the 5, and what is the borrow? The borrow is the number 1. 1 is being borrowed, right? And who is borrowing out? The 2 is borrowing out this 1. And who is borrowing in? The 5 is borrowing in. So remember that. There's a borrow in and there's a borrow out. Okay? So that's first concept. Okay? So borrow out of the left column is the borrow in of the right column. So of course, one guy is the lender and one guy is the receiver. Right? So borrow out and borrow in. Simple concepts over here. Not too hard. Okay. Now, let's look at the subtraction rules. 0 minus 0, naturally, 0. Right? Okay. Let's go down to this one, the second line. 1 minus 0. 1 minus 0 is easy. 1. Right? Okay. 1 minus 1 is a 0. Now, for the first 3 lines, Was any borrowing required? Just from logic, I shouldn't be teaching you this. Just from natural logic, you should be able to figure out, yeah, there's no borrowing required. Now the last line, 0 minus 1. This is the tricky one. 0 is a small number, right? 1 is the large number. So 0 minus 1, the answer will be 1, but you've got to borrow a 1. All right, that's the rule. That's where students get caught out. Okay, just remember that. Okay, all right. Let's now plot that. Let's now plot whatever we have done. Let's now plot that on our thing. So I'm going to just write down document camera, zoom in. Okay, so what was yesterday? Week 7, lecture 1. What was yesterday's date, guys? 3rd? So that was a lecture on half adders and full adders, all right? So now we continue, week 7, lecture 2, and today is the 4th of May. All right. So we are doing half subtractors. Well, we are doing full and half subtractors. All right. So let's have a look at what we had to draw. Okay, so it's a truth table, and we've got to find out. So basically, we take our rules. This is the difference. They call it the D, and we have the borrow out. Okay, 0, 0, 0, 1, 1, 0, 1, 1. All right, guys. Okay, so that's the difference. Sometimes they call it just the D, and this is the borrow out, BO. Right? There's BO and there's BI. Okay, so 0 minus 0, the same rules which we discussed early on. 0 minus 0 is 0, borrow, no borrowing required. 0 minus 1, well, 0 minus 1, let's skip that for a second. Let's move on to the third line. 1 minus 0, you have a 1. Is any borrowing required? No. 1 minus 1, you have a 0. Any borrowing required? The answer is no, right? And 0 minus 1, that was the tricky one, the one which we discussed early on. Where 0 minus 1, the difference will be 1. Obviously, there is a difference of 1 between 0 and 1. 0 minus 1, let's talk about it in normal decimal now, in normal mathematics. 0 minus 1 will give you a negative 1, right? So we know the difference is 1, right? But in order to facilitate that in digital logic, you need to borrow, because 0 was a smaller number. Okay. Now, from this, what we pick up is, let's look at this guy here. Let's look at the difference line, guys. What can you tell me about the difference line in terms of Boolean algebra? Can you give me an equation? What does it look like? Does it look familiar or similar to any of the particular thing? Let's cover the BO line up. Let's cover the B line up. And have a look at the truth table, A, B, and this line. What can you tell me? What does it look like? Just by observation, you should be able to say, yes, this looks like XO. Right? So you have A, XO, B. All right, so I think things are looking very similar to yesterday. That's the good news. Very, very similar to yesterday. Now, what can you tell me about B out? Borrow out. Well, borrow out would be what? What can you tell me, guys? From your sum of products, if you apply the sum of products, what do you identify? There's only one, so the sum of products will be very easy to do, right, for this particular system. There will be A bar and B. What did we use? Using sum of products. Well, whichever method, even if you want to put that on a Carnot map, that's all good. All right? So that's our function. How does this differ from yesterday? What did our sum say? Our sum equation yesterday. What did that have? Come on guys, look it up. The sum had what? A XOR B, same, right? So what did our carry out? In that case we had carry out. What was that? For a half adder. For a half adder, carry out was AB, AOB. AOB or ANB? ANB, eh? Okay, A and B. And only in this case, the borrow out is A bar and B. See, it's just a subtle difference. But the concept is the same. So that's what I'm trying to teach you. If you can learn half adders and full adders properly, this will be a very simple system to handle. All right, guys. Now, let's now take it to another level now. Let's now consider, let's skip, so go back here. And then, okay, so we filled this out, right? Okay. In the end, this is the circuit. Those two equations result in this circuit. So I'm not going to waste time and redraw the circuit. This is the circuit. Okay? From the truth table, we are able to find the half adder circuit. The half subtractor circuit. Now, again, notice that this circuit can only handle 2 bits. Bit A and bit B. 2 bits. Right? There's nothing coming in. So there's no facility allowing it to connect to anything else. It's an isolated system. That's the problem. Same problem with half adders. What is the problem with half adders and half subtractors? They can only handle 2 bits, bit A and bit B. No connectability to another system. We have to develop that. Right? We can't bring in a carry out of something else and plug it in here. Okay, so there's in terms of, let's say, if you guys are familiar with computer or something else, there's no expansion port over here. You can't expand the system. We have to artificially do it. Okay, all right. Now, so that's the circuit: A XOR B, A bar and B. Simple circuit. All right. And of course, if somebody were to do this circuit, you can build it using a NAND realization. Isn't that correct? You can build it using NAND. Okay, right. So that's the block diagram. We show it in form of a block diagram because we want to reuse it over and over again. All right. Drawing that is complicated. Drawing the block diagram is easy. Okay. Now, let's talk about a full subtractor. A half subtractor can only handle 1 bit subtraction. Right? There were 2 bits, but the number of bit in the end is 1. Yeah. What do we mean? What do we mean over here? Let's focus slightly more. I was only saying there's bit A and bit B. Okay, bit A minus bit B, right? Fair enough. Or bit A plus bit B for half adder. But the final answer can only hold 1 bit. The final sum or the final difference has only capacity for 1 bit, right? Okay. Now, consider the sum 1 0 minus 1. 1 0 minus 1 in binary, right? So how do we do this? Well, we've got to borrow, yeah, like how I showed you earlier on. So you borrow out from this 1. You take the 1 in over here, borrow in over here. 1 minus 1 is, right, 0. And then you have a 0. So you have a difference over here. So we now introduce you to something new called the concept. We introduce you to the equation for the full adder, right? So we were showing you over here the concept for a full subtractor, right? In the full subtractor, we have added a new expansion port, so to say, to allow it to expand. And that is known as the borrow in. So we introduced now, early on, when we did this truth table in our exercise book, we could only handle 2 bits going into the system, right? Now we want to create a system which will handle 3 things. So A minus B minus borrow in, right, is equals to difference and borrow out. Borrow out of the left column is the borrow in of the right column. Same thing. Right, let's now do this exercise over here. Let's now look at the truth table for our full subtractor. We are moving towards full subtractor now, guys. Okay. full subtractor. Okay, so we have A, B, borrow in, you have the difference, and you have borrow out. 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 1, 1, 1, 0, 0, 1, 1. All right, guys. Okay. All right. Now, the way we look at this is like this. 0 minus 0, and there was no borrow in, right? 0 minus 0, and there was no borrow in. I want you to, if you are confused, we are looking at this equation. Let's see this equation. This is the master equation of our full subtractor. A minus B minus borrow in. Okay, remember that. What are we doing? We're doing A minus B minus borrow in. Okay. 0 minus 0 is 0. Okay, you have to do 2 bits at a time. You can't do 3 bits. Right? Then the answer minus again a 0 will give you a 0. Right? Now, was any number bigger or smaller? No. So we just find the answer to be 0 over here, because there's no borrow required in that case. Now, 0 minus 0 is 0. Fair enough. Now, that answer of 0 minus a 1 of borrow in would be 0 minus 1 is difference of 1 and the borrow of 1. Yeah, okay. Now 0 minus 1 is a 1, right? 0 minus 1 is a difference of 1 and a borrow of 1. 1 minus 0 is again 1, but that borrow stays. Set? All right, now, next one. 0 minus 1 is a difference of 1 and borrow of 1, and 1 minus 1 is a 0, right? So the difference of 0 is there, but the borrow stays. Right? You guys can track it in different ways. Some people write it out over here. They make another third column to track. Okay. Or some people do this line first, and then the answer of that line, then they bring it into this. Okay. Now, 1 minus 0 is 1. No borrow required. So this is still 0. 1 minus 0 is 1. No, sorry, on this line. 1 minus 0 is 1. And then 1 minus 0 is, again, 1. And no borrow was required. Okay, let's do this one. 1 minus 0 is 1, no borrow required. Again, 1 minus 1 is 0, no borrow still required. 1 minus 1 is 0, right? No borrow required. 0 minus 0 is still 0, still no borrow required. 1 minus 1 is 0, the answer is 1, no borrow required. Now 0 minus 1 is 1 and the borrow is 1. So this is the truth table for our full subtractor. And how did we do it? We did it using A minus B minus borrow in. Okay, so we're introducing something over here, right? We want to develop the full subtractor. Now, of course, let's now look at the truth table for D. And we did this yesterday as well, guys. Okay, I'm just looking at the D column over here. All right, we end up something like that. All right, I'm pretty sure you know you're familiar with how to translate this D column into this Carnot map over there. Right, in this case, there's no groups. And if you remember, didn't we find this similar pattern yesterday? Yeah, we found a similar pattern yesterday when we were doing the full adder. So the difference for the full adder is D is equal to A XOR B XOR C. You guys can, I think, did we do the proof yesterday of the full adder whereby, did I show you the proof yesterday? Did Rahul show you the proof? That you would be saying A, but this is A bar, B bar, B in. This is A bar, B bar, B in bar, right? When you do the Boolean algebra, you'll eventually find that you can arrange it in this manner. And I think yesterday the proof was there. Okay, all right, we did a proof of this yesterday. Okay, so same thing applies over here. So you're starting to see the similarities between the two. All right, there's one more left. Let's now talk about B out, borrow out. All right, okay. Okay, I'm going to just show you, just for your learning purposes, I want to show you, I flipped over. I put B and B in on this side, and I've put A on this side. Okay, just for fun. Okay, all right. It'll give you the same answer in the end, 0, 0, 1, 1, 1. Okay. Of course, I'm looking at the truth table over here. Looking at the truth table over there, all right. So what do we get? We get all right, and then we can loop that around. We can group those two. We can group those two. All right, so let's have a look at this. This will be B and B in. This is A bar and B in. This is A and B. All right. Okay. So if you look at yesterday's lecture, right? There was a particular part where we wanted to rewrite that. So this is where yesterday's lecture comes up, and I'm going to finish in the next few minutes because I just want to have a quick chat about your exam tomorrow. If you look at yesterday's lecture, the sum was all fine. The sum we were able to do, all right? The sum we were able to do, and one homework over here. If you could write the homework for the difference is, if you could find the minimum sum of products from that Carnot map, and then find how the MSOP links to this. This is how did we get an XOR gate over here, right? Now the next homework is, there's two homeworks over here, and this will be coming in the final exam, or maybe test number 2, is how can we represent this one here, the borrow out, using XOR gates. Using XOR gates. How? So two homeworks. One is the difference. How did we find that particular system when the Carnot map is telling us some other answer, and we are talking about XOR maps, because Carnot maps never give us XORs, right? Carnot maps only gives us N's and O's, right? And the other homework is homework number 2. Note it down, guys. Is how do you re-represent this or rewrite this after some, this is already simplified according to the Carnot map, but how do we re-manipulate it in order to get some XOR over there, right? How do we get XOR in the system? And if you look at yesterday's lecture, and I've already seen your lecture on the lecture capture, right? You guys did cover a particular proof of how you went from the Carnot map solution to an XOR solution. When I say XOR solution, I mean in the end you came up with an XOR, all right? Something along these lines over here. All right, there we go. So something along those lines. So you had some Carnot map, you had to rewrite it, and then eventually you were able to find the XOR. So the same thing applies. So that's your homework, guys, for difference equation. Eventually, let me just switch over and finish off very quickly. Right, we've done this. Eventually, we come up with something known as a full subtractor. A full subtractor. The truth table which you did was full subtractor. You have A minus B in, right? So B in, A and B. You have, if you explode that, you get two half subtractors. So you're able to combine two half subtractors in order to make a full subtractor, and that's our circuit of a full subtractor. All right? Okay? All right, guys. Now, with regards to tomorrow's test that will be held, tomorrow's test shall be held at the normal 014-024 lecture room. It will be 50 minutes long. Everything, including the half header, will be coming in the half and full header will be coming in the midterm exam. Have a look at last year's exam. If you look in the Moodle shell, you might be able to find the 2019 test and the 2021 test, I'm pretty sure. How many of you have been able to locate the 2019 midterm test? How many of you have been able to locate the 2021 midterm test? Okay, it's somewhere there. If you look for it, you'll find it, all right? But I'm not saying the same questions will be repeated. I'm just referring you to the standard of questions which is expected. That is the standard, all right? Okay, I won't copy and paste the questions, but maybe I might manipulate it further, right? Okay, so yeah, and please be on time. Do not come late because you'll lose that time. We only have a lecture room booking for 1 hour, all right? Any other questions, guys, with regards to the test? Sorry? Yeah, it's at 5 to 6, 5 p.m. till 6 p.m., right? So please be on time. Please try and be in the lecture room by 10 minutes to 6, 10 minutes to 5, all right? Don't waste your time. Please be in the room and try and separate yourself from your neighbor, leave one space gap, and all that sort of thing, so that we don't waste time in, sometimes the TAs will come and they'll probably ask you, if you're sitting beside two of your friends, they'll ask you to move to another seat, and that'll waste your time. Those few minutes is very important. Don't waste time in the test. Try and be fast, all right? If you've done all the lecture exercises and all the tutorial exercises, you should be fine, all right? It's not going to be an absolute killer exam, just a half killer, all right? Just to shake you up. Okay, all right, set. So we'll see you tomorrow, okay?